Model analysis. You see, in order to predict the performance of hydraulic structures or hydraulic machines before constructing or manufacturing them, models of the structure of machines are made and tests are performed on them to obtain desired information. Before you build hydraulic machines, it's important to know how will this machine perform before you construct them, because if you go ahead constructing them before knowing all of this, you might realize that your design fails. So it's important we take analysis, and we do analysis by building models. That's actually what model. So a model is a small scale replica of the actual structure or machine. And the actual structure or machine is actually called a prototype. Though not in all cases is the model smaller than the prototype, but in most cases, the models are actually smaller structure compared to the prototype. Now, the study of models of actual machines is actually called model analysis. So let's look at the following advantage of dimensional and model analysis. One, the performance of hydraulic structures or machine can easily be predicted even before they are manufactured. So before having your prototype already, you can tell how this machine or structures are going to perform. Again, is that the test performed on the models can be used for obtaining advanced and useful information about the performance of the prototype. You want to know some other important information. What you have done on your model, you can use that by similitude to predict what the prototype will do or get extra information about the prototype. Also, the merit of alternative designs can be predicted with the help of model testing. The most economic and safe design may finally be adopted. And lastly, with the help of dimensional analysis, a relationship between variable influencing a flow problem in terms of dimensionless parameter is obtained. This relationship helps in conducting tests on the model. So, types of similarities. Similitude is defined as the similarities between model and prototype in every respect. Well, three types of similarities must exist between model and prototype. The first one is the geometric similarity. So, geometric similarity is said to exist actually between the model and the prototype. The ratio of all corresponding linear dimensions in the model and prototype are actually equal. We see that the length of prototype over length of model is same as breadth of prototype over breadth of model, and diameter of prototype over diameter of model, and is equal to the scale ratio. We can also use height, whatever measure the meter actually. You can use height of prototype over height of model as well. Again, we have the area ratio, which is area of prototype over area of model, which is the square of the scale ratio. And we have the volume ratio, which is volume of prototype by volume of model. And this is the scale, that is the scale ratio raised to power 3. Let's take the next similarity, which is kinematic similarity. So next we have the kinematic similarity. This simply means the similarity between the motion of the model and prototype. Well, there will be kinematic similarity between model and prototype if the ratios of the velocity and acceleration at the corresponding points in the model and the prototype are the same. Now, for kinematic similarity, we have it that velocity of prototype at point 1 over velocity of model at point 1 is equal to velocity of prototype at point 2 over velocity of model at point 2. And that's known as the velocity ratio. Also, for acceleration, acceleration of prototype at point 1 over acceleration of model at point 1 is equal to acceleration of prototype at point 2 over acceleration of model at point 2. And this is known as the acceleration ratio. Okay, so dynamic similarity, the third type of similarity. Dynamic similarity means the similarity of forces between the model and prototype. Thus, dynamic similarity is said to exist between the model and prototype if the ratio of the corresponding forces acting at corresponding points are equal. Well, for dynamic similarity, we have it that the inertial force of the prototype over the inertial force of the model is equal to the viscous force of prototype over viscous force of model, and which is equal to the gravity force of prototype over gravity force of model, on and on the various forces we have. So this is not just the only thing. Continuously, you can compare with other forces also. We have elastic forces and the rest. Also, the direction of the corresponding force at the corresponding point in the model and prototype should be the same. In our third type of similarity, which is dynamic similarity, we establish that we have dynamic similarity between model and prototype if the corresponding forces at corresponding points in the model and prototype are actually equal. This simply means that we are trying to say that, for instance, the viscous force in the prototype is equal to the viscous force in the model, and then the gravity force in the prototype is equal to the gravity force in the model. The inertial force in the prototype is equal to the inertial force in the model. All type of forces will be equal. That's what we're trying to say. It's difficult to actually achieve that when carrying out similarities between model and prototype. Very, very difficult. So models are actually designed the base of the force which dominates the flow. So I'm going to look at what force actually dominates this flow, and in that I will now choose the model law we want to use to design or bring out the similarity between the model and prototype. Well, there are different types of model law. We have the Reynolds model law, Froude model law, Euler model law, Weber model law, and the Mach model law. So the Reynolds model law, if flow situation where inertial force or viscous force dominates, the similarity between the model and prototype is established using the Reynolds number. And this is the Reynolds number now. Density of the model, velocity of the model, and length of the model over viscosity of the model, which is density of prototype times velocity of prototype, the length of prototype over viscosity of the prototype. I gave this relationship in our dimensional analysis. So the Reynolds number for the model must be equal to the Reynolds number for the prototype. The following are some phenomena for which Reynolds model law can be sufficient criterion for similarity. One is the motion of airplanes, motion of incompressible flow in closed pipe, motion of submarine completely under water. Also is the flow around structures and other bodies immersed completely under moving fluid. So let's take example 1 now. An oil of specific gravity 0.92 and viscosity 0.03 poise is to be transported at the rate of 2,500 liters per second through a 1.2 meter diameter pipe. Tests were conducted on a 12 cm diameter pipe using water at 20 degrees C. If the viscosity of water at 20 degrees C is 0.01 poise, find the velocity of the flow in the model and rate of flow in the model. Well, let's solve this question now. We understand that in the actual sense, it was oil we want to transport. So that stands as our prototype. So specific gravity of the oil was given as 0.92. We can go ahead to get the density of the oil. We know that specific gravity is density of oil over density of water. So we can say density of oil is equal to density of water times specific gravity of the oil. So that will give us density of water is known as 1000 times 0.92. So this is 920 kilogram per meter cube. Okay. Again, we are given the viscosity of the prototype, since that's the viscosity of the oil. That's given as 0.03 poise. So I want to convert to Newton seconds per meter square. So just multiply by 10. That will be 0.3 Newton seconds per meter square. Again, we are given the discharge of the prototype, and that is 2,500 liter per second. I will convert to meter cube per second, just dividing by 1000. That's 2.5 meter cube per second. Again, we are given the area of the prototype. So that's the area of the pipe used to transport. They want to use to transport the oil. We are given diameter, sorry. So diameter of prototype is given as 1.2 meter. Let's get the area. The area, okay, of the prototype will be pi d square over 4. Since it's a pipe, so this will be pi times 1.2 square over 4. Come back with the answer. Okay, next is the model now. Tests were conducted on a 12 cm diameter model. So the diameter of the model now is given as 12 cm. Convert to meter, that's divided by 100. That will be 0.12 meter. So the area of the model will be given as pi d raised to power 2 over 4. And that will be pi multiplied by 0.12 over 4 square. Come back with the answer for that. Again, what else are we given? We are given the viscosity of water. The viscosity of water is given as, which is the model, because water is what we want to use. It's given as 0.01 poise. So we can say this is times 10, 0.1 Newton seconds per meter square. Okay. Now, we are asked to get, let's calculate firstly the area of this model. So this is 1.13 meter square, and this is 0.0113 meter square. Okay. Now, let's go ahead to calculate the velocity of the flow in the model. Before we do that, let's have the velocity of the flow in the prototype. We know that this charge of prototype is area of prototype times velocity of prototype. So we can say velocity of prototype is discharge of prototype over area of prototype. So that's how we got the area actually. What's the discharge of prototype? We're given 2.5 divided by the area of prototype 1.13. So this will give us 2.5 divided by 1.13. This 2.2 meter per seconds. So we are using Reynolds number here, flow in pipes actually. This is one of the phenomenon where we can use Reynolds number. So we have it that density of model, velocity of model, and then length of model over viscosity of model should be equal to density of prototype, velocity of prototype, length of prototype over viscosity of prototype. Well, we don't have length here. Okay, but let's proceed. I will come back to say what I want to say. Now, the next is to rearrange now. We have it that velocity of model over velocity of prototype is equal to density of prototype over density of model times viscosity of model over viscosity of prototype times length of prototype over length of model. Very simple. All I quickly did here was to bring this to this side. So it becomes Vm over Vp, and brought this down and took this up. So whatever is at the numerator comes at the denominator, and whatever is the denominator comes at the denominator when you have equal to between two formulas or between two relationships. So next is to put in our values. But remember, we don't have length here. What we have is diameter. We can also change this to diameter, since the scale ratio can mean length of prototype over length of model, or diameter of prototype over diameter of model. So I will quickly change this to diameter of prototype over diameter of model. So very, very simple. Now let's proceed. What's the density of the prototype? Density of water is given to be 1000. We said that. But this prototype is supposed to be the oil, and the density is 920. So 920 all over density of the model, that is water, 1000, times viscosity of the model. The model is the water. The viscosity is 0.1 all over the viscosity of the prototype, which is the oil. The viscosity is given as 0.3, okay, times diameter of the prototype, that's 1.2, over diameter of the model, which is 0.12. Velocity of the model is what we're looking for, all over velocity of the prototype. We've gotten that already using the discharge, that is 2.2. So very simple, we can say that Vm over 2.2 is equal to, let's evaluate this now quickly, 920 multiplied by 0.1 multiplied by 1.2 all over 1000 times 0.3 times 0.12. So this is 3.067. So we can therefore say that velocity of model now is equal to 2.2 multiplied by 3.067. Okay, 2.2 multiplied by 3.067, 6.75 meter per second. If we have the velocity of the model, we can take the second question we asked to solve in this question. That is to say, the rate of flow. The rate of flow simply means discharge of the model. Discharge of the model is what we associate, rate of flow of the model, which is equal to area of the model times velocity of the model. So what's the area of the model? We've done that already. That's why we solved for the area already. 0.01113 multiplied by the velocity of the model, we've gotten that 6.75. So we can say our answer here would be 0.0113 multiplied by 6.75. This is 0.076 meter cube per second. So that's all for this question. Froude's model law. When gravitational force dominates in any flow situation, in addition to the inertial force, the similarity of flow between model and prototype can be established using the Froude number. Some of the phenomena for which Froude model law can be sufficient criterion for dynamic similarity to be established in the model and in the prototype are: 1. Free surface flow, such as flow over spillways, sluices, etc. Secondly is the flow of jet from an orifice or nozzle. 3. Where waves are likely to be formed on the surface. And 4. Flow where fluids of different densities flow over one another. Open surface flow is flow over an open environment. Okay. Next, according to the Froude model law, we have that the Froude number for the model must be equal to the Froude number for the prototype. And this is the formula for the Froude number. Let's just take an example here now. Example 1. A clever design of the front of a ship is to be tested in water basin. A drag of 12.2 Newton, that's the drag force, is measured on the 1:20 scale model when towed at a speed of 3.6 meters per second. That means the corresponding speed of the prototype ship and the drag to be expected. Let's bring out the parameter given to us here now. First and foremost, we are given the drag force on the model. Drag force on the model to be equal to 12.2 Newton. And then we are given our scale ratio, let's say length of prototype over length of model to be equal to 20/1, or which just equal to 20. Or length of model or prototype is 1/20, whichever way you want to write it. Again, we are given that the velocity of the model is given as 3.6. That's the speed at which the model is being towed. Okay, first and foremost, we write that velocity of model over square root of L of model and G of model is equal to velocity of prototype over L of model and G of prototype. L of prototype, G of prototype. But we know gravity is the same for both model and prototype. So that can be eliminated in this formula. So we are left with velocity of model over square root of length of model is equal to velocity of prototype over square root of length of prototype. Okay, since we are looking for velocity of prototype, we have it that velocity of prototype will be equal to velocity of model multiplied by square root of length of prototype over square root of length of model. We can as well write that as this: velocity of model times square root of length of prototype over length of model. What's the velocity of model given to us in this question? 3.6 multiplied by square root of, what's the length of model over length of prototype? That's given as 20. So if we evaluate this, we have 3.6 times square root of 20. That's 16.1 meter per seconds. So we have it that the inertial force is simply mass times acceleration. And this can be density times volume times velocity over time. We've done this in our dimension where we're getting those dimensionless numbers. And this is density times area times length, because volume is area times length, then times velocity over time. This can be readjusted into density times area times L over T times V. Our area actually can change to length square. So this is density times length square times, this can be velocity. Velocity times velocity. So we have it that our inertial force can be calculated using density times velocity square times length square. So please take note of that. So I'm simply going to say now that the drag force for the model over drag force for prototype, or drag force for prototype over drag force for model, is equal to density of prototype velocity square for prototype times length of prototype square all over density for model, velocity for model square times length of model square. Well, we have it that since water is what is used, density of the prototype, or density water is used for the prototype and model, they will cancel out. So we have velocity of prototype over velocity of model squared times length of prototype over length of model squared. Actually, this is the inertial force for prototype and inertial force for model. So it's equal to drag force for prototype over drag force for model. Now let's put in our values now. The drag force for the model, for the prototype, is what we're looking for. For the model, it is 12.2 given the question. Velocity for the prototype is given as 16.1 over the velocity of the model is given as 3.6 squared times length of prototype over length of model, we have it to be 20. This is 20 square. So we can say, let's evaluate that now. Okay, this will be 16.1 in brackets over 3.6 all squared times 20 squared. That will give us Froude number, a drag force, sorry, for the prototype over 12.2 being equal to about 8,000. Then we have it that the drag force For the prototype will be 8,000 times 12.2. That's 97,600 Newton.